Hi guys, it's Mr. Holding here, and this video is quickly explaining what Punnett squares are and what they're used for. So Punnett squares are a way that we can look at the genotype of two parents and determine the chances of offsprings having any combination of different things. So first of all, we're going to look at complete dominance. So the first thing we're going to look at here is a homozygous dominant versus a heterozygous dominant. So if we look here, I'm going to use these alleles here. So it doesn't really matter what we're referring to. It could be eye color, could be hair color, could be whatever. But we're going to put capital A as the dominant allele and little a as a recessive. So homozygous dominant, homozygous meaning the same, dominant meaning dominant. So we'll put the big A there and the big A there. So this is one person. So this could be the father, for example. Okay, and then the heterozygous dominant. So hetero meaning different. So we need one dominant and one recessive, and this could be mum, the mother. Okay, for example. Now all we want to do is use this Punnett square to cross it. So A with A, so we end up with, this is one possible offspring, a homozygous dominant. Another one here is big A, so that one across, that one down. Okay, it should be an A there, not an R. Okay, big A, little a. Now remember, we always put if there's a capital, you put that first. You always put the dominant one first, irrespective of what order. And then the same one here, big A, little a there. Okay, so now we want to analyze our Punnett square, and we look at it, and we want to look at what fraction of each of we've got. So first of all, we can count the number of squares. There's 1, 2, 3, 4. If I want to look at the results and the chances of an offspring being a homozygous dominant, I simply put the number of squares with that trait, with that combination, over the total. So in this case, it's 2 over 4. And of course, we reduce that down to 1 over 2. Okay, and then to add further to that, if I go, well, what's the chances of that? You can simply convert that into a percentage, which is, of course, 50%. So if these two, this father and this mother, produce offspring, there's a 50% chance that it's going to be a homozygous dominant. That might be eye color, hair color, whatever. It doesn't matter, but that's just the example. Okay, likewise with big A, little a, it's a 2 out of 4, which equals 1 over 2, and again, that's a 50% chance. So this is an example of a complete dominance. Okay, it's important to be able to get through this process here and follow how to get results. So the next example we're going to look at is the case of codominance. In this one, we're going to talk about blood type. So I'm going to use capital I with a superscript A for A-type blood, capital I with a superscript of B for B-type blood, and then a little I for O-type blood. Now the reason why I put these two as capitals is because they're both dominant. Okay, they're as equally dominant as each other, but they're both dominant over O. Okay, so it's important. When we look at them here, we do our cross the same way. We do our Punnett square. So I've got I superscript A with little I there. So this might be, again, this might be the father, and this one might be the mum, and then we cross them as we had before. So I've got big, that one there, that one there. So we've got A and A, so that blood type's going to be A. Next one, I've got that one there, big A with little O, so it's that's dominant over that, so it's going to be an A type blood. I've got my scenario here. I've got an A and a B, okay, both on dominant, so this is a situation where codominance comes into play, and then I've got this one here. Okay, so all I do is match them up, making sure my capital is always at the start. So I'm quickly going to go through here and add it up. Again, I'm just going to do, there's 4 spaces and work out how many is that. So it's 1 over 4, which equals 25% chance of it being this guy here. 1 over 4 of that one equals 25%. 1 over 4 of that guy, again 25%, and Of course, the last one will be 25% as well. So to get with these two parents with their unique, their two alleles, there's 25% chance of getting either of any of these. Okay, and we know here that this guy here is going to be is going to experience codominance. Okay, you will sometimes see these where they've got. So, for example, here I've used I to share the dominance. So occasionally, you see them. They might use A, B, and then a lowercase o. So for the dominant A, the dominant B, and then the recessive O. I like it this way to show that these two are codominant here. Okay, and you'll see that in a moment when I look at when we look at the next type of dominance, incomplete dominance. Why I prefer this one here. Okay. So for incomplete dominance, we're going to look at snapdragons, and generally snapdragons are a flower that they're either red or white. Or pink, and we're going to find out how we can do that. So let's pretend we've got a purebred red and a purebred white. Okay, so doesn't matter which is which, excuse me, but we're going to cross them W, 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 W. Okay, so we've got all four of those. Okay, the reason why I mentioned earlier that I like to use a common letter when I'm referring to codominance as opposed to this is because when I see two different letters next to each other, I tend to assume incomplete dominance, so it's a sharing. Whereas if, as we had earlier when we had the blood type, when I see that, I refer to codominant, so meaning that these two are equally dominant, so they have to both be expressed, whereas in this scenario, they are shared. Okay, so I do that. I want to go with my results. Okay, so my results, 4 out of 4 is 100%. Okay, that one's a fairly easy one. There's more complex, but all I'm going to do each time is count the total number, and that's what it's out of. And then go, okay, well, I'm looking for the percentage of RW, 1, 2, 3, 4. 4 out of 4 is 100%. Okay, there are more complex ones, which I'll do in another video, but hopefully that gives you a brief introduction of how to do Punnett squares for both dominance, codominance, and incomplete dominance. Okay, thanks very much. Bye. Sorry, gents, missed one more example that I need to do, and that's sex-linked inheritance. So we talked about colour blindness before. Okay, in colour blindness, the gene is attached to the X chromosome. Okay, and capital B, which is dominant, is normal eyesight. So normal eyesight is a dominant, which is why colour blindness isn't as common. And it's little b indicating it's recessive. Okay, so colour blindness is actually recessive, attached to the X gene. It's actually far more common in men, and we'll see why now. So right now we've got a cross between a father who doesn't have colour blindness, so you can see that by the capital B, and a Y, and now the Y doesn't code for anything because it's a different type of gene. Okay, but the Y denotes that it's a male, and then capital B and lowercase b, because this is dominant, then the mother isn't colourblind, she has normal eyesight. But when we cross it, okay, dominant, homozygous dominant. Oh, it's a bit ugly there, XB, so you've got a father with normal eyesight. Okay, you've got a mother who's a carrier, but she's got normal eyesight. And then over here, we've got a male child who has the recessive gene, but then has a Y. Okay, because of that, because there's no dominant gene on another X, and the Y doesn't carry the gene, then this person is going to be colorblind. Okay, so as you can see down here, I've gone and taken my results here and calculated the fraction, what chances, and also the percentage here. Okay, and if the question is, what is the chances of this father and this mother having a child who is colorblind? Well, that's the only one there. okay, they have a 25% chance of having a male child who is colorblind, okay, and we can see that there because on the X there is the recessive gene, and because he's only got one X because he's male, there's nothing to counteract that, so therefore he's going to show that, and that's why colorblindness is more common in men than in women, okay, because it's a recessive order linked to the X chromosome. Now, there are other ones that are on the Y, but we'll do those in class. Now, for the second time, hope you found this useful, and see me if you have any issues. Thanks, bye.